I have put together this video to discuss the 4 parts to a typical synthetic experiment: the synthesis, workup, purification, and then product analysis. The ultimate goal is to teach students about the design of a synthesis experiment. After watching all of my videos, I hope that when students read a synthesis, they can appreciate and understand its design. As well, when students have to design their own experiment, these videos should give a bit of direction on how to start. Organic synthesis experiments in a research setting can be classified into 2 general types. The first type is the design-based experiment, where there's a target molecule and either a novel synthetic method to the target molecule must be developed, or a better one developed than what's found in the literature. This route is popular with chemists interested in making molecules that are expected to have useful properties. While the second type is called the guided inquiry experiment, also known as the discovery-based experiment, where the reactants and reagents are mixed together and then the goal is to figure out what's made. Chemists pursuing this route are typically interested in deciphering the mechanism to a reaction. Students often underestimate the usefulness of library resources. In the design-based experiment, one would typically go to the literature to see what's been done. Perhaps a similar molecule or even the exact molecule is used for the search. The procedure is evaluated based on feasibility with chemicals and equipment available, reactants, reagents used, time required to perform the reaction, and how much product the reaction yields. Percent yields are usually given in the literature. Therefore, if you know how much you want to have, it's possible to calculate approximately how much starting materials are required. It may also be the case that there is no procedure available for the exact target molecule, so a chemist would use their chemistry knowledge and adapt a literature procedure leading to a similar, perhaps more common, product to their situation. So for example, let's say we're trying to make this particular ether, and using our nucleophilic substitution reaction knowledge, we would propose that it would have come from these starting materials. In the literature, there is this particular synthesis that I could adapt to. A note of caution that when someone pursues this route, they should check the physical properties of the reactants and products, if available, because the literature workup might not work for the proposed experiment. Say, for example, the product melting points are different, and therefore one might be a solid at room temperature while the other is a liquid. Proposing a procedure isn't all that daunting if you know what the steps are. Number 1, based on your background knowledge, propose a reaction equation and then balance it. It's important to figure out the byproducts at this stage so that you can account for them in the next step. 2, for each of the reactants and reagents, look up their physical properties and safety information. 3, determine the amount of reagents and reactants required, as well as how and when they are added. In the real world, we try not to waste chemicals, and therefore a trial reaction is usually performed on a small scale. And then once we're confident it works, then perform on a larger scale. 4, determine how the reaction is monitored for reaction completion. 5, determine how the excess reactants are quenched, if necessary, and the reaction is worked up. 6, consider how the crude product will be purified. And finally, 7, consider what the appropriate methods are for product purity and identity analysis. Now, in contrast, guided inquiry experiments are heavily dependent on product analyses to identify what products are made. Then, using an understanding of the chemistry and further physical chemistry experiments on determining rates and rate-determining steps are conducted. A reaction mechanism would be proposed for how the product is made. Now that you've heard about the 2 common types of organic syntheses, you may be wondering what type your teaching lab experiments follow. Almost all of our experiments are neither design-based nor guided inquiry experiments. The teaching lab experiments are called expository experiments, where students follow a procedure, much like a cookbook, and make a predetermined product. Despite guided inquiry and design-based experiments being quite educational for students, since they encourage research, problem-solving, data analysis, etc., we don't have many in the labs at the second-year level because of a lack of resources, in particular time, in the lab and outside of the lab. Many students at the second year require a bit more training in the laboratory techniques and library research techniques before they can be independent enough to work on the projects in these formats. As well, you typically also need other analyses, such as NMR, for your products in the guided inquiry experiments. And for the large volume of students in our introductory courses, it's just not feasible. So you'll have to wait until third year organic, Chem 3390 and 3580, to have a try at a few more of those experiments. So now we'll take a look at each of those 4 parts in a synthesis and discuss their significance. At this stage, the reactants and reagents are added together and the reaction occurs. The 4 major considerations at this stage are what reagents are used, amounts of reagents used, and how they are delivered to the reaction mixture, what solvent to use, and finally figuring out if heating is required. In terms of what reagents are used, that would be based on the reaction chemistry and perhaps what the literature suggests, if available. If we are to think of all reactions as having equilibria, being able to proceed forward or backwards, how do we ensure that a reaction proceeds forward? We can use Le Chatelier's principle and stress a reaction by either adding excess reagent or removing product. In some of the lab program's reactions, the product may precipitate out, which effectively decreases the product concentration in solution and helps to drive the reaction forward. Alternatively, sometimes a byproduct is eliminated, such as a gas or a solid precipitating out, which can also help drive the reaction forward. In the scenario where a reagent is used in excess to drive the reaction forward, one has to decide which reagent is used in excess and which is the limiting reagent. For both of these, consideration must be placed into the cost of the reagent and if the reaction can be monitored based on the limiting reagent. For the excess reagent, thought should be put into if and how it will interfere with the workup and product isolation step. After deciding on which reagent is limiting and which is in excess, we have to decide on how much excess should be used. The first time a reaction is performed, we usually keep the quantities in the milligram range. Once a percent yield has been figured out, then for subsequent trials, we can calculate the limiting reagent quantity based on the percent yield and how much product we want to obtain. To decide on how much excess reagent to use, I'll incorporate it into a more general and inclusive discussion relating to the material in the experiment design video. So let's look at an example where I'm going to propose a procedure to make this acetal. I would first go to the literature database such as Google Scholar, SciFinder Web, and perhaps even Web of Science to search for this product, and see if there are any papers on its synthesis. Assuming the exact synthesis is not in the literature, and from having the chemistry knowledge, I could retrosynthetically propose that it would have come from the acid-catalyzed reaction of this aldehyde and this diol. It is likely that I might be able to find a similar product in the literature, so I could adapt the procedure for what I need to do. But as mentioned previously, when procedures are adapted, the product and reactant physical states must be considered to determine if the workup steps are transferable. Let's say I would like to develop a new procedure for this acetal synthesis. I propose that I can use ethylene glycol and p-tolualdehyde along with some tolusulfonic acid as a catalyst to get to this product. Acetal formations are reversible reactions, so I have to make sure to drive the reaction forward. Luckily, there are several ways to do this. In the chemistry literature, an equilibrium constant of 0.0125 moles to the minus 2 for the acetal formation of acetaldehyde and ethanol has been reported, and I can't find a value for my particular reaction. However, I can use this number as a starting point for my system. Although I would think that my system would be more favorable to the product because it is only a bimolecular reaction as opposed to a termomolecular reaction, and therefore it's entropically more favorable. You can try to figure this one out by counting the molecules involved in my reaction versus what's in the model reaction, and then figure out how entropy relates to free energy and K. So to drive a reaction forward, I can either remove product or use an excess of one of the starting materials. Let's look at removing a product or byproduct first. In this reaction, water is produced as a byproduct. So how can we go about removing water from the reaction to drive it forward? If the conditions allow, we can use a setup called the Dean-Stark apparatus. In the distillation flask, I have the starting materials, but also a solvent of toluene. The toluene is very helpful in this reaction because water has a boiling point of 100 degrees Celsius. However, with toluene present, an azeotrope can form, which has a boiling point of around 84 degrees Celsius. Which means that the toluene functions as a carrier solvent to get the water out of the reaction at a lower temperature. So you can imagine that the mixture of toluene and water ascend this inclined sidearm, and then when it hits the condenser, the mixture drips down to this trap area. One of the neat things about using toluene is that it's immiscible with water, so in liquid form we'll see two layers, layer on the bottom and toluene on the top. So over time the trap fills, and then the excess top layer of toluene will trickle back into the reaction flask. There's a stopcock as part of the trap so that we can drain the trap should it be getting too full of water. In theory, the advantage of using the Dean-Stark apparatus is that it doesn't require the use of excess reagents, since the reaction would be driven forwards anyway by the byproduct removal. As you can imagine, the Dean-Stark apparatus wouldn't be appropriate for starting materials with boiling points less than water, since they, and not water, will end up in the trap. In this case, we'll need to drive the reaction forward by another, more common method, and that is using excess starting material. To calculate how much excess reagent is required to drive a reaction forward, I'll need to use the equilibrium constant and the ice table. Remember that from general chemistry? So I will use a 1 to 100 mole ratio of the aldehyde with alcohol as a starting point. In solving for X, I calculated 0.66 moles, which means a 66% yield. Because the K is so small, I'll need a lot of excess to drive this reaction forward, but keep in mind that the 0.0125 moles to the minus 2 is a rough and lowball estimate. So now, let's consider a 1000 times excess of one of the starting materials. That will give us a 93% yield of product at equilibrium. That being said, we still have to consider the feasibility of using that much excess, cost, and how easy it is to remove. So in this case, 1 mole of aldehyde, which is about 120 grams, is used to make approximately 0.9 moles of acetal, which require 1000 mole of ethylene glycol, about 62 liters of ethylene glycol. So this is an obvious case where it's not feasible to use that much excess. Even the 100 times excess, 6.2 liters, is on the huge excess and waste side. If I were to do this, I would probably use something like 10 times excess, about 600 milliliters. I chose the ethylene glycol as an excess because it is easy to remove by washing in the workup step, and it's inexpensive compared to p-tolualdehyde. In the planning stages, one has to consider how and the order with which the reagents are added. How the reagents are added is based on the reactivity and their physical states. Sometimes the reagent will have to be dissolved in a solvent first before addition to the reaction, or sometimes the reagent is added dropwise to control the reactivity. In terms of when the reagents are added is based on the reactivity. The most reactive component, sometimes could also be a catalyst, is usually carefully and slowly added last. In most reactions, a solvent is used. Since a solvent doesn't participate in the reaction, why use it at all? There are several reasons why solvents are used. 1. Solvents are used to dissolve the starting materials, maximizing their mixing. You can imagine that if you are working with solids, the reactions would only take place at the solid surface, and that's very inefficient. 2. Some reactions are sensitive to the reagent concentrations, and using a solvent dilutes their concentrations. 3. Helps ensure that the reaction temperature is up to the solvent boiling point and can be maintained constant. 4. For exothermic reactions, the solvent acts to absorb the heat. 5. As you may remember from your Chem 2210 material, an appropriate solvent can stabilize an intermediate, which will help promote a particular mechanism. How much solvent should be used? This is a question of what concentration would the reaction occur at. Of course, the concentration is related to the rate of the reaction. The more concentrated this reaction, the faster the reaction. We typically perform the trial reaction at about 0.1 molar, and then on repeat trials optimize the concentration. What do we mean by optimize? Aiming to get good product yields and purity while minimizing reaction time. So wouldn't not using solvent be following green chemistry principles, and is it possible to not use a solvent? Well, there are some reactions which are performed without an additional solvent, and these are called neat reactions, and usually involve the intimate grinding together of the reactants. Sometimes one of the reagents is a liquid and doubles as a solvent, so it can be used to dissolve all of the starting materials, although there is debate in the green chemistry field as to whether these are considered solventless reactions. Many of the organic reactions require heating. When you look at the various pieces of glassware, boiling flask, Erlenmeyer, beaker, they all have their purpose in the lab. Beakers have a wide mouth, and we never use it for a reaction with organic solvents because of rapid solvent loss. Erlenmeyers have a smaller opening and therefore minimizes some of the solvent loss, so it is typically used for crystallizations and sometimes for reactions. Now, if we were to heat up a reaction for an extended period of time, we want to ensure that solvent loss is kept to a minimum. So that's where the boiling flask and round bottom flask with the ground glass joint comes in. Research labs have a piece of equipment called the heating mantle, which is used to support and heat a round bottom flask. An alternative is to put the flask into a sand or oil bath. The goal of all three is to provide even heating. Unfortunately, we don't have heating mantles in the teaching lab, and in inexperienced hands, oil and sand baths are very messy to work with. So our compromise is to use a boiling flask, which has a flat bottom to maximize contact with the hot plate. The round bottom and boiling flask's ground glass joint allow us to insert a condenser so that the reaction mixture can reflux. Some reactions need reflux periods in the tens of hours, such as overnight. Then it's very important that the tubing is secured around the condenser inlet and outlet joints so that it doesn't pop off and lead to flooding of the lab. For reactions conducted using smaller quantities, a test tube can be used as a reaction vessel and placed in one of the previously mentioned baths. This may come to a shock to many of you, but there is a difference between the temperature that's read on the hot plate versus the temperature of the reflux. As a simple example, the hot plate reads 275 degrees Celsius. On there is a beaker of water and a beaker of mineral oil, which have been heating for the same amount of time. The water has been boiling for the past 10 minutes, and we're reading a temperature of 95 degrees Celsius. Meanwhile, mineral oil, which boils at a much higher temperature, is reading 164 degrees Celsius. So keep in mind that when the solvent is refluxing, you know that the solvent temperature is near its boiling point. Don't assume that it's whatever is read on the hot plate. So why does a reaction require heating? All chemical reactions have an activation barrier, and therefore energy, in the form of heat, is required to get over this barrier. When heat is supplied to a reaction, it's giving kinetic energy to the molecules so that when they collide and react in the form of bond breaking and making. I would discuss equilibria in another video. However, by heating a reaction, sometimes we drive the reaction towards product because the heating can be removing a byproduct, such as water. Some chemical reactions can lead to two or more products, depending on the conditions used. As a simplified diagram, with some reactions there might be a low activation barrier to get to a product, while others may have a higher activation barrier to get to a more stable product. In these two cases, the reaction temperature helps control which product is made. To get to the thermodynamic product, the product of lower energy, heat is supplied. While to get to the kinetic product, the lower activation energy product, less thermal energy is made available and is performed under cold conditions. Placing the reaction mixture under an ice water bath can keep the reaction temperature at around 0 degrees Celsius. However, with mixtures of various organic solvents and dry ice or liquid nitrogen, other sub-zero temperatures can be achieved. Some reactions are extremely exothermic, and they are typically done under cooler conditions so that the reaction doesn't get out of hand, leading to undesirable side reactions. One common question that I get is something to the effect of, how long should we wait for a reaction to finish? The question of how long a reaction takes relates to the kinetics of the reaction, and that is based on how reactive the starting materials are, the order of the reaction, which relates to the concentrations, and the mechanism of the reaction. For example, we expect unimolecular reactions to take place faster than a bimolecular reaction. In the real world, if it's the first time that we're doing a new reaction, we typically don't know how long it'll take. We typically have to monitor the reaction to determine when the reaction is over. Of course, in many of the reactions performed in the organic teaching labs, I've done that part, so students are told to let the reaction occur at a specified time. I just mentioned a phrase that may be new to you, monitor the reaction. What does it mean? By monitoring, we mean to make observations on the progress of the reaction. In this example, A plus B goes to C, where A is the limiting reagent. Over time, the concentration of C increases, while A decreases and eventually lead to 0. So to monitor this reaction, we would typically be looking for the time where A is completely gone from the reaction. The common methods used to monitor the reaction can either indicate the presence or absence of a compound, and usually not the quantity. Although with NMR, you might be able to make a guess of the quantities based on relative integrations of the various compounds. Once again, something that you might do in the third-year organic labs. There are 3 common ways to monitor a reaction. In this retroscopic method, a sample of the reaction mixture is removed, and then maybe a workup is required before NMR or IR analysis. There might be a functional group with the molecules that one could be looking for, say for example the disappearance of a carbonyl group. Thin layer chromatography, which is the more common method because it is likely faster and cheaper than some of the spectroscopic methods. For this method, a sample of the reaction mixture is removed at certain time intervals, say once every 5 to 10 minutes, and then placed onto a TLC plate. It is usually co-spotted with the starting materials. The plate is developed, and the disappearance of the limiting reagent from the product lane is a sign that the reaction is complete. So in this example, it will take about 15 minutes for the reaction to finish. A side note that the eluent is optimized at some point before the reaction to ensure that the right conditions are used to monitor the reaction. Gas chromatography is just like TLC in principle, and if the reactants, reagents, and products are liquids, then one can use GC instead of TLC to monitor the reaction. So when the reaction is completed, it's time to move on to the next 3 steps: workup, product purification, and product analysis. The workup is the name given to the process where the reaction is complete and it's time to isolate the crude product. Sometimes a very reactive reagent is used in excess, and it must be reacted with, or quenched, before proceeding to isolate the crude product, just because it could lead to undesirable side reactions or are dangerous to work with. Just to note that the term quench may also be used when a reaction is stopped, before all limiting reagent supply is exhausted. Most reactions will either have an excess of acid, base, oxidizing agent, or reducing agent. Therefore, to quench, the opposite of these will be added to get to neutrality. For example, an excess of acid will be neutralized with base. An extraction or washing is usually used at some point in the workup, either to crudely isolate the product, extraction, or to remove the starting materials or byproducts, washing. During an extraction or washing, there is a separation of 2, ideally immiscible layers, an organic and an aqueous. With choices such as dichloromethane or ethyl acetate, we can have the organic layer be on the bottom or the top of the biphase. This is useful for the procedural perspective. Say, for example, the reaction mixture is dissolved in ethyl acetate. This mixture can be washed continuously with an aqueous layer, and the washing solvent be easily removed. In contrast, if the reaction mixture was in aqueous solution, then the product can be extracted with dichloromethane. In the video on the left, my mixture is dissolved in dichloromethane, and I'm washing that layer with the clear colorless aqueous layer. In the video on the right, my mixture is dissolved in less dense ethyl acetate, and I'm extracting that with a blue aqueous layer. Notice all the effort that the dichloromethane layer requires to properly wash it. So the take-home message is, be careful on solvent choice because it could lead to more work than necessary. Having said that, sometimes we have no choice but to do this. I'll talk a bit about this in the Equilibria video. After an extraction or washing, the organic layer will typically require a drying step to remove any residual water. The liquid layer is washed with brine, saturated salt solution, and then further dried with a drying agent. If the drying step is skipped, water, and whatever is dissolved in the water, would remain to contaminate the product. At this stage, the crude product needs purification because we know that if a sample is contaminated, the physical properties will change, and therefore the product identity can't be confirmed. As well, sometimes one product made will be the starting material of another reaction. Therefore, if the sample is impure, the quantity measured for the reaction may not accurately reflect how much is there. The method with which we purify would depend on the physical properties of the product. You've learned to crystallize solids and distill liquids. In more advanced chemistry labs and research setting, column chromatography is another common technique. It is a little costly and takes a bit too much time, so that's why we won't see it in our second-year teaching labs. However, in principle, it's similar to TLC, so you should be able to easily understand how it works. The final product isolated will have to be analyzed for identity and purity. You've used techniques of GC, IR spectroscopy, melting point, and boiling points to analyze your samples in the past, depending on its physical properties. The other spectroscopic methods, such as NMR, are very useful as well, but we don't have access to the instrumentation at the second-year level. So with that, this video is concluded. I hope you now understand what parts make up a chemical synthesis experiment, as well as have a better understanding of the necessity of each part. Take a moment, put this video on pause, and reflect on what you've learned in this video, because quite a bit of content was covered. I started this video describing the 4 parts to any chemical synthesis. I then gave a brief glimpse at what 2 major types of organic synthesis experiments there are, as well as how experiments are planned. With each of the chemical synthesis parts that I discussed, I broke each section down and discussed what decisions are involved at each stage. For example, what reagent quantities are used, is heating required, how do we go to isolate the product, what analyses can be used to determine the identity of the product.